Chapter 13 in Calculus 3 is all about vector calculus. The first section, 13.1, is about vector fields, and this is video number 1. For those of you who plan on pursuing physics and engineering degrees, you will be doing a lot of vector calculus. This said, I am neither a physicist nor an engineer. So, I will be showing you mainly the tools that you will be using in physics and engineering, and a few applied examples taken out of the book, because that's my limit of physics and engineering knowledge. But let's start with what a vector field is. You may recall that a vector is an object with both direction and magnitude. For example, 4 miles north is a vector, or 13 miles southeast is a vector, or something like that. And vectors have all kinds of applications, some of which I'm a little familiar with, some of which I'm not. For example, you could have a map that shows a vector representing wind in the direction and the speed in which it's blowing, and at each point on the map there would be a different vector. Or you could have one for current flow in an ocean. At a certain point in the ocean, the water's flowing that way at this speed, whereas at a different point it's flowing this way at a slightly smaller speed. So a vector field is basically any way that you can assign a vector to each point in a plane. Here's another example about gravity. Let's say that we put a really heavy object here at the origin that is so massive, like the sun, that it draws in all the objects around it unless there's some other force acting otherwise, such as the path of the Earth, which is preventing it from being pulled into the sun. But if the Earth stopped revolving around the sun, then it would just slowly be sucked into it. So hooray for the Earth's orbit. But anyway, if you have a mass in the center of a plane at the origin, then each point would be drawn towards it. But the closer it is, the stronger the force is that's pulling it in. So for example, if we had a point really close to that mass, the vector pulling it in would be pretty strong. Whereas if we had a point further out, it would be pulling it in, but with less of a force. And then the further out you get, the smaller the vector would be. And this would apply to every point on the plane. For example, if we drew a circle around here, then a circle around here, then every point on this circle would be being pulled inward towards that mass in the center with the same force. Of course, if we went out further, then the points out here would be pulled in, but with a lesser force. I can't tell if that's a shorter arrow than this one. But my point is, we could find a vector for every point on this plane. Now, that's not the formal definition of a vector field. The formal definition of a vector field is actually quite simple. We're going to define a vector field first in 2 dimensions. All right, this comes directly off of page 755. So we're going to let D, capital D, be a region in R2. A vector field on D, and by the way, D may be the entire, one moment. Okay. They actually define the vector field on the entire plane, R2. They'll allude to D in a moment. But a vector field on R2 is just a function. Now in the book, whenever they write something to represent a vector, they use boldface. I really can't draw bold on here and distinguish it from not bold. So to represent something as a vector, I always draw a vector arrow above it. So that's a function, but it's a vector function. So it's a function f, and it's a function f that assigns a vector. Trying to make sure I don't leave out anything important. A 2-dimensional vector, because we're living in R2. A two-dimensional vector to every point in D. So D is its domain, basically. That function is usually written as vector function f of x comma y, because the input to this function is an ordered pair, a point on the plane, and the output is a vector. And we could write that vector a few different ways, but we're going to write it as some function which we'll call p of xy, as that gives us the I component of the vector, plus another function, we'll call it q of xy, that gives us the j component of the vector, assuming that you know that I is the unit vector one direction in the x direction and in the positive x direction, and j is the unit vector in one unit in the positive y direction. When we stretch this out to 3 dimensions shortly, we'll append a third function, we'll call it capital R, and it will be the component for k. Speaking of components, these functions are called the component functions. A component is just a part of a vector when you write it, well, in component form. Now, you are eventually going to do calculus on vector functions, so it's important to talk about continuity briefly. Without redefining continuous, we'll just say that if we define what it means for a vector function to be continuous, then the continuity of the vector function is 100% dependent on the continuity of its component functions. So a little FYI, we're going to state this without proof. The vector function f is continuous. I want to say if and only if. I'm pretty sure it's if and only if. Yeah, it is if and only if. If and only if P and Q are continuous. If you're going the pure math route, when you get to a course called topology, you'll learn a lot more about what it really means to be continuous. It's quite fascinating. And what if and only if means is you can't have one without the other. For example, if the vector function is continuous, then its component functions are continuous. But if the vector function is not continuous, then one or more of its component functions are not continuous. Or equivalently, you could say, if this function is continuous, then so are those. And if these functions are continuous, then so is this. Almost as if it were a definition. It's not a definition, the definitions are separate, but they do coexist. Either you have both or you have neither. Now, in the next video, we're going to take a look at sketching a vector field in 2 dimensions, which with technology is a lot faster, but some of them you can do manually.